Start, sir.
Welcome to live session 3, the final live session of the course on optimization in chemical engineering. So today, based on your input on the forum, so we have decided to review the use of artificial variables in case of linear programming problems. So in particular, we'll talk about two methods, two-phase method and a bigger method. So we'll take examples and try to demonstrate the working of the method. Okay, you are already familiar, you are aware that the exam for the course has been postponed due to the difficult situation that all of us are going through. So please take good care of yourself and your family. Stay home, stay safe. The evaluation policy, I mean, this will be valid only as and when this situation improves and when you write exam. But these are available on the website, so be aware of this. So we have already said this in our previous live session as well. The final score is average assignment score plus exam score. Average assignment score is based on your 8-based assignments. 25% of that will be taken, and exam score is 75% of the exam score out of 100. And to be eligible for a certificate, you must obtain 10 out of 25 in the average assignment score and 30 out of 75 in the exam score. So now let's discuss the use of artificial variables in case of linear programming problem. So the situation will arise in certain linear programming problem. It won't appear always. So let us first review the basic steps of linear programming problem. So I assume that you are already you are all familiar with this. So I perhaps don't go into the very details, but let me outline all the key steps. So first thing we do is express the linear programming problem in standard form. Then we start with an initial basic feasible solution in canonical form. And then we can set up the initial W. Now we use the inner product rule to find the relative profit coefficient Cj bar. And then if all Cj bar less or equal to 0, then the current basic feasible solution is optimal. Otherwise, we select the non-basic variable with most positive Cj bar value to enter the basis as basic variable. So this is with respect to maximization problem. So if you are solving minimization problem, your choice will be governed by Cj bar greater or equal to 0. And instead of selecting the non-basic variable with most positive Cj bar, we will select the most negative one. Now apply the minimum ratio rule to determine the basic variable that will leave the basis and become non-basic variable. Now these operations will do again and again until you obtain the optimality conditions. So until the optimality conditions are reached, you will do this repetitively in series of tables. Now the problem happens when the basic feasible solution is not readily available. You have seen that we express the linear programming problem in standard form. So you have a canonical form. And then in most of the cases, you have a ready-made basic feasible solution to start the simplex method. But simplex method will not start until and unless you have an initial basic feasible solution. So when initial basic feasible solution is not available, we have to do something so that we obtain an initial basic feasible solution. Because without initial basic feasible solution, the simplex method of linear programming problem will not proceed. So the first step will be to obtain a basic feasible solution. It may happen that there doesn't exist any basic feasible solution. In that case, you will conclude that the linear programming problem is infeasible. So, while solving a linear programming problem, after converting the problem in its standard form, that means all the constraints are converted as equality constants by putting surplus variables, slack variables, etc. All the variables are non-negative, and the right-hand side vector is non-negative. So that is what you mean by converting the LPP in its standard form. That constants are all equations, variables are all non-negative, so greater or equal to 0 type, and right-hand side vector is non-negative. So if there is any negative element in the right-hand side, you have to multiply both sides by minus sign to make it positive. So after converting the linear programming problem in its standard form, if you are unable to obtain initial basic feasible solution, you have to follow certain steps so that either you obtain an initial basic feasible solution and go ahead with the solution of the problem, or you conclude that the given linear programming problem is infeasible. So you stop with that conclusion. So what you do is, when a basic variable is not available, so first what you do is you examine each constraint for existence of a basic variable. If basic variable is not available, a new variable is added to act as a basic variable. So I basically add an artificial variable to act as basic variable. So after doing this, you will see that all constants will have a basic variable and the system will be in canonical form. So after you have put surplus variables, slack variables, etc., you examine each constant for existence of a basic variable. If basic variable is not available, you add an artificial variable. Now, after visiting each constant this way, you will finally notice that a basic variable is available for all constants now, and the system will be in canonical form. So the basic feasible solution can now easily be obtained. Now, the problem is that the basic feasible solution that you obtain now does not belong to the original linear programming problem, because it becomes basic feasible solution to the artificial problem that you have obtained by attaching artificial variables to the original problem. So if I can obtain a basic feasible solution to this artificial problem so that all the artificial variables are 0 there, then of course the basic feasible solution for the artificial problem becomes same as basic feasible solution for the original linear programming problem. So the key state is as follows. When basic feasible solution is not available, we introduce artificial variables to obtain the initial basic feasible solutions. Once initial basic feasible solution is obtained, simplex process can start. But now the goal of the simplex process will be that you force these artificial variables to 0 in a later steps. So just to get an example, let us say we consider this linear programming problem. So add slack and surplus variable. This doesn't need anything, means any variable. But to convert it to standard form, you must multiply this equation, this constant throughout by -1, so that right hand side vector is positive. So this is the linear programming problem in standard form. But note that there is no basic variable for this constant as well as this constant. Note that S2 cannot be basic variable, because if I consider x1, x2, x3 as non-basic variables, that means their values are 0, x1, x2, x3 equal to 0, x2 become -3, which violates this. But there is no problem with this. If I set x1, x2, x3, s1 becomes basic variable. So less or equal to type constant doesn't create problem, but greater or equal to type creates problem because of this minus sign of this surplus variable. So now let us introduce artificial variable. Note that we had only basic variable for the constant 1, where if I set x1, x2, x3 equal to 0, I get S1 equal to 11, which satisfies this. So that becomes a feasible solution. I mean, in terms of only S1, becomes S1 satisfies greater or equal to non-negativity restriction. But constant number 2 and the constant number 3 requires 2 artificial variables. So for constant number 2, we introduce artificial variable R1, and for constant 3, we introduce artificial variable R2. So let us call this artificial linear programming problem, artificial LPP. Note that this is in canonical form. I can set x1, x2, x3, s2, 0, x1, x2, x3, s2, 0. So note that I have 3 equations. You have 3 equations, and you can solve only for 3 variables. You have 7 variables here. So you need to set 4 variables to equal to 0. So you have to choose 4 non-basic variables. So if I choose x1, x2, x3, and s2 as non-basic variables, they become 0. And then I have a feasible solution, s1 equal to 11, r1 equal to 3, and r2 equal to 1. So this is a basic feasible solution for this artificial problem. For this artificial linear programming problem, this becomes a basic feasible solution where x1, x2, x3, s2 equal to 0. That means they are non-basic variables, and s1, r1, and r2 are basic variables. But this basic feasible solution is not a basic feasible solution for this original linear programming problem, because R1 and R2 are not 0. and R1 and R2 are not part of this original problem. I have introduced artificially into this problem just to obtain the initial basic feasible solution. So if I can obtain a basic feasible solution for this problem, where R1 and R2 equal to 0, that basic feasible solution becomes a basic feasible solution for this original problem as well. So that is what should be the driving force for solution of such problem. So there are two methods we'll discuss. One is approach 1, big M method to handle these artificial variables. Another is two-phase simplex method. So let us start with big M method. We'll review this big M method again towards the end. So as I told you that this artificial variables R1 and R2 must be forced to 0 because they are not part of the original problem. So I can formulate the linear programming problem as shown here, where I am changing only the objective function in such a way that I penalize the presence of R1 and R2. Here I am solving a maximization problem. So I subtract a large number multiplied by R1 and a large number multiplied by R2 from the objective function. M is a large number, that is 100 or 1000. So note this, for maximization problem, if I take the objective function like shown, so that the presence of R1 and R2 are penalized, the optimizer will force R1 and R2 to be equal to 0, so that this ZVs becomes maximum. Because any non-zero value of R1 and R2 will only subtract substantial amount from Z, because n is large number and positive number. So your optimizer will force R1 and R2 to 0. So if I obtain a solution to this linear programming problem, which is the artificial linear programming problem, and in the solution my R1 and R2 are 0, then of course this also becomes solution of the original linear programming problem. Because we just drop R1 and R2 from this equation, so this becomes the original linear programming problem in standard form. So that is the key principle of big M method. So all you do is you basically change the objective function such that you penalize the presence of R1 and R2, and you go ahead as usual with the simplex method. Because you have the initial basic feasible solution ready now, which is x1, x2, x3, and s2 equal to 0 non-basic variables, and s1, r1, and s2 are s1, r1, and r2 are basic variables. So you can go ahead with the regular simplex method with this objective function. And if you go with this with values, say m equal to 100, you will see that you will reach optimality, and the optimal solution will have R1 equal to 0, R2 equal to 0. So that solution will also be valid for original linear programming problem. Now let's consider approach 2, which is two-phase simplex method. Now in two-phase simplex method, the first phase, we will solve an auxiliary linear programming problem to either get a basic feasible solution or conclude that the given linear programming problem doesn't have any basic feasible solution and this is an infeasible linear programming problem. So if I obtain the initial basic feasible solution in phase 1, I will proceed with phase 2. Otherwise, I will conclude that the given linear programming problem is infeasible and will stop. So the phase 2 will be, we will solve the original linear programming problem starting from the feasible basis or initial basic feasible solution that we have found in phase 1. So phase 1 is to obtain the initial basic feasible solution, and phase 2 is to solve the linear programming problem with the basic feasible solution that you have found here. So this phase 1 will be solved, we'll see, with a modified objective function, but not similar to the bigger method. And the phase 2 will continue with the original objective function. So let's go through this in some detail. Again, let us consider the same problem. So we have the given linear programming problem. It's a maximization problem. So what we do is, you first introduce the artificial variables. So that you can obtain initial basic feasible solution as usual. So x1, x2, x3 and s2 are non-basic variables. s1, r1 and r2 are basic variables. Now, in the phase 1, I solve this linear programming problem. I solve these constraints with an objective function which says you minimize R1 plus R2, sum of all the artificial variables that I have introduced. If I introduce only one artificial variable, you will minimize, say, R1 only. If I introduce 5 artificial variables, you will minimize R1 plus R2 plus R3 plus R4 plus R5. So in case of phase 1 auxiliary linear programming problem is, the objective function will be minimize sum of artificial variable introduced. Now what is the minimum value? The minimum value is 0 because all these variables are constant to be greater or equal to 0. So this sum, minimum value of this sum is 0. So note that this is a smart way of obtaining a initial basic feasible solution from this problem, which is valid for this problem. So what happens when you solve this auxiliary linear programming problem with this objective function, but when optimality is achieved, you see that the objective function value f is not 0. If it is not 0, it means that at least one or more artificial variables have positive value. They cannot have negative value. They are all constant to be greater or equal to 0. So if the minimum sum of the artificial variables is not 0, it means that there are at least one non-zero artificial variables in the optimal solution for this problem. It means that the original linear programming problem is infeasible. There doesn't exist an initial basic feasible solution for the original problem. So let me stress upon this. When you formulate this auxiliary linear programming problem, the constraints are all put in the standard form, right? And then objective function is changed to some of the introduced artificial variables. See, the theoretical minimum possible is f equal to 0. So when the optimal solution is obtained for this particular problem, you look at the solution. If f is 0, that means both R1 and R2 are 0. So that solution is basically basic feasible solution for the original problem. But if the optimal solution for this problem shows that f is non-zero, that means at least one artificial variable has non-zero value. Your conclusion will be that the basic feasible solution for this problem or the optimal solution for this problem cannot be a basic feasible solution for the original problem because all artificial variables are not zero. It means that the original linear programming problem is infeasible. So then your calculations stop. So phase 2 will proceed only when we have obtained the basic feasible solution. That means the objective function value for the phase 1 is 0. So if that is the case, the phase 2 will start with the basic feasible solution that is obtained in phase 1 with changed objective function. Change means the original objective function. So basically in terms of tableau, you will basically take the final tableau of phase 1. That becomes the initial tableau for phase 2. The objective function is changed and the column corresponding to artificial variable is removed. That's it. Here I have shown A1 and A2 as artificial variables. You can, please read it as R1 and R2. Or note that A1 and A2 is artificial variables here. So now let's take an example. So I'm taking this example and I'll go through this all the tables that are necessary. So this is the linear programming problem. To make things simple, I am taking a different problem than the one that we have been discussing. There are three equations here. I have two equations. Note the presence of this less or equal to type constant. And greater or equal to type constant. So this greater or equal to type indicates that you have to introduce artificial variable. This is all right. So this becomes is a maximization problem. This becomes a linear programming problem in standard form. So all constants are equations, right hand side vector greater or equal to 0. All variables are greater or equal to 0. Problem is basic feasible solution is not possible. You don't have ready-made basic feasible solution. If you have two equations for variables, you can solve only for 2. If I say x1, x2 equal to 0, s1 becomes -2, which is not possible. Introduce artificial variable. Now I have two equations, 5 variables. I can solve only for 2 variables. If I set x1, x2, and s1 equal to 0, that means if I choose x1, x2, and s1 as non-basic variable, and r1 and s2 becomes then basic variable, I have a basic feasible solution because r1 equal to 2, s2 equal to 4. So I have a basic feasible solution. But again, this basic feasible solution is not for original LPP. This is only for this artificial LPP because R1 is 2. So what we do? We solve the auxiliary LPP. So we solve the auxiliary LPP where R1 needs to be minimized. Objective function Z equal to R1. Again, what is the minimum value of R1? So it can be 0. And if minimum value of R1 is 0, then the solution that we obtain here becomes basic feasible solution for the original problem. But if the minimum value of R1 is non-zero, then the original LPP is infeasible. So this needs to be solved using regular simplex method. Note that the objective function is minimization of R1. Either you can go ahead with this minimization of R1 or you can write maximization of minus R1. So we use the same construction of table that we have discussed during regular lecture. So note this coefficient of the objective functions. See x1, x2, s1, x2, r1. Only r1 is there, so 1 here. So these are the coefficient matrix. See 1, 1, minus 1, then 0 for s2 and 1. Similarly, 1, 1, 1, 1, 0, 0 for S1, and then 1 for S2 and 0 for R1. You can also write like this here, that x1 plus x2 minus s1 plus 0 into s2 plus r1. This will become easier. Otherwise, you understand that this is how you have to write. So basis is r1 and s2. And then you find out the CJ bar, find out the minimum ratio. And since we are minimizing the objective function, we will consider most negative CJ bar to decide which variable will enter the basis. Now here, both are at -1. So any one of these two can be considered. We have considered this. Find out the minimum ratio, and the minimum ratio and CJ bar says that x1 enters and r1 leaves. The objective function value is 2. So now just repeat the process. Find out CJ bar. When you find the CJ bar, you see all CJ bars are all these are 0 and this is 1. So all CJBars are greater or equal to 0. So you are solving a minimization problem, so we'll take most negative one. So we consider most negative CJBar. But all CJBar greater or equal to 0 for minimization problem will mean that the optimality condition is achieved. Now the basis is x1 and s2. So R1 is non-basic variable and R1 equal to 0. Z equal to 0. So we have obtained the basic feasible solution for the original problem. So this solution in the phase 1 becomes the original problem, the basic feasible solution for the original problem. So what we will do now is we'll consider this table as the initial table for the phase 2. Basically, we'll drop this column and change the objective function. So these coefficients will change. Let us see how. So this is my original problem. Maximize z equal to 2x1 plus x2. And this is the final tableau of the phase 1. So note that I have basically dropped this column. This entire is taken. Okay. But this will change. In the previous case, your objective function was R1. So that's why x1, so this was basically 0 into x1 plus 0 into x2 plus 0 into s1 plus 0 into s2 plus 1 into R1. That was the objective function. So now it is 2x1, maximize 2x1 plus x2. So this is 2 for x1, 1 for x2, 0 for s1, 0 for s2. So that's why you get 2 here for basis x1. So note that the same basis vector. So again, compute CJ bar, minimum ratio as usual. Again, we are maximizing. So most positive CJ bar will decide which variable will enter. So S1 enters and S2 leaves basis. Repeat the computation. So you must do the matrix operation to get this in canonical form. Compute CJ bar. And you see that CJ bar, all CJ bar are less or equal to 0. You are solving a maximization problem. So all CJ bar less or equal to 0 signifies that optimality condition is achieved. Because there is no variable which will enter basis and improve the objective function value. Because all CJ bar are less or equal to 0. So they are only, if we choose anyone, that is only going to deteriorate, decrease, or at the most it will remain unchanged, the objective function value. So we have actually obtained the optimal solution. So x1 equal to 4 and s1 equal to 2. That is the introduced by variables, and basically x2 equal to 0. In terms of solutions over x1 and x2, your x1 equal to 4 and x2 is non-basic variable, x2 equal to 0 is the solution. So 2x1 plus x2 So 2 into 4 plus 0, 8 is the optimal solution. This is for maximization problem. So for minimization problem, it will be minus 8. The same x1 equal to 4 and x2 equal to 0 will be the solution. But the objective function will be minus 2x1, right? So it will be minus 8. So this is how a two-phase simplex method can be used. In the phase 1, you find out basic feasible solution or conclude that the original LPP is infeasible. And in the second phase, phase 2, you basically go ahead with the solution once the basic feasible solution is obtained in phase 1. Now look at big M method. So big M method, basically you use the regular simplex method by taking this problem. So take the large value of M such that the solution is, you obtain the solution with R1 equal to 0. So we can solve using the regular simplex tables that we discussed or you are familiar with already. But let us do one thing. Let me just show you how the use of lin probe. So let me, instead of showing those tables, let me show you the output of the Matlab function lin probe, which solves linear programming problem. But what I'm going to do is I'm actually going to solve this problem. I'm not going to solve the original. I'm going to solve the original problem by solving this problem, as if I'm doing by hand computation, right, using the tools. Why I'm saying is because, see, you actually do not have to introduce, you do not have to solve the, you have to convert the original LPP in this form and then make use of lin probe. You can directly use lin probe. You can use the original formulation and can directly use the LP, can directly use the lin probe comment to solve the problem. But since my objective is to show how the big M method works, so I convert the original LPP to the form according to the big M method and then solve this particular form using lin probe. So lin probe actually doesn't understand then that it is solving a linear programming problem which does not have a ready-made basic feasible solution. But if you use lin probe and the original formulation, MATLAB will internally understand that it doesn't have a feasible solution. So it will actually, if you, without you knowing it, it will, you can know it, but without you knowing it, MATLAB will silently find out the basic feasible solution, go ahead with the process and ultimately give you the solution. So let us solve the LPP in this form so that I understand that bigger method works or not. So you know the original formulation, as you know the command for lin probe. So this is the objective function vector. This A and B is like X equal to B, X less or equal to B. So that is inequality constants. These two is like A equality into X equal to B equality. So there's a equality constant. So that is what we have actually. Less or equal to, don't have F. So A and B we do not have. And this is lower bound or upper bound for the variables, which you can use. Sometimes you may not use it as well. But you can use it because we are restraining it to be greater or equal to 0. So you can use it actually. So note, so here I am writing this, you know, so that it becomes easy for you to form this matrix and vector, particularly this matrix. Note that I have put 0 into S2 here, 0 into S1 here, 0 into R1 here. So my variables are variable 1, variable 2, variable 3, variable 4, and variable 5. So you have that is important, right? So because you will have 5 elements in the first row and also 5 elements in the second row in this matrix. And they must be pointing to the same variable. So this is 1, 1, minus 1, 1, 0. 1, 1, minus 1, 1, 0. For x1, x2, s1, r1, and s2. So that sequence is important. So here you have 1 for x1, 1 for x2, 0 for s1, 0 for r1, 1 for s2. So this is how we form this equality matrix. B equality is a vector 2, 4. Objective function vector, coefficient. Vector of coefficients of objective function. Again, that is important. So x1, x2, s1, r1, and s2. This is s2. So variable 1, variable 2, variable 3, variable 4, variable 5. So you must consider, say, r1 as variable 4 everywhere. So on and so forth. So 2, 1, 0, minus 1, sorry, minus this m, and then 0. But since we are solving a maximization problem and MATLAB solves minimization problem, I take minus 2, minus 1, 0, 100, and 0. Lower bound I take 0. Let us take, say, all upper bounds as 10. Then call the linprobe. So you obtain this solution. x1, right? 4. x2, 0. s1, 2. r1, 0. So r1, we obtain 0. That is important. And s2 equal to 0. So basically, you get back the same solution that you obtain in two-phase using two-phase method. And note that how this method has forced this R1 to be 0, so that this solution is valid for the original LPP. Okay, so this is what I had to say about this two-phase method. So similar exercise you can also do for two-phase method. The formulation that you have obtained in phase 1, solve the LPP in that form. Then we'll understand that it is actually minimizing the sum of artificial variables. Again, you do not have to break the problem into such two formulations and solve using linprobe. The original form itself can be solved using linprobe. But to understand it better how this two-phase simplex method works, I suggest that you do exercise the same way I showed you for bigger method. Similar exercise can be done for two-phase method. Okay, one of you asked us to show how fsolve works and also the online toolbox. That is a graphical user interface. The best way to use it will be just try yourself. So it's basically is a user-friendly graphical user interface where you can write these equations, where you can enter the numbers. Okay, that should not be a problem. If you face problem, we can post one slide containing, capturing the screenshots and can put on the forum. Okay, to show you how to make use of MATLAB command fsolve to solve a set of nonlinear simultaneous algebraic equations. Here is a simple example. So I have, let's say, these equations, simultaneous equations in 3 variables, 3 equations, 3 nonlinear equations. So the MATLAB comments are all very similar. Okay. This fsolve is basically a function that is available with optimization toolbox. So basically, this solution is posed as an error minimization problem. So it's posed as an optimization problem and been solved. So what you do is you basically first define the function where you will write these equations. You may have 3 equations or 300 equations, really doesn't matter. So You write the equations. So F is basically a vector of all these equations. And then simply call the solver fsolve with initial guess. So this is the minimum argument, minimum syntax that you will be using. So this is the name of the function where you describe this your system of equations, which for these three equations is written here. And x0 is your initial guess. So if you have three variables, so you must give three values. And then simply call the solver fsolve. And the solution is often here, x. So please do some hands-on to get a better feel of how this is done. So this way, actually fsolve finds very good use in several chemical engineering problems, say particularly when you solve steady-state equations. So steady-state equations, oftentimes we'll have the, we'll set that, see the ddt term equal to 0, and we will be ending up with a set of simultaneous nonlinear algebraic equations. So to finding out steady-state conditions for, let's say, CSTR, bioreactor, and similar many such processes in chemical engineering, you will make use of fsolve to solve nonlinear algebraic equations, mass balance equations, so on and so forth. So there is one more question on the one more question is from, okay, that was the question from Aditya Sharma. Now Shruti Roy, she's asking, are optimization techniques cost effective and how can they be used in biomedical domains? I think it's a very general question, but what is important in our question is, are optimization techniques cost effective? Yes, it is. So because the optimization techniques that we have been talking about requires only simulations, right? So these are not experimental optimizations, right? So there is like experimental techniques like response surface methods, factorial design, so on and so forth. When you do design, when you follow design of experiments to do certain set of experiments, and then do statistical analysis, follow response surface methodology techniques, and come up with optimum conditions. So that is one way of doing this, by obtaining experimental obtaining optimal conditions for a process, is going through a set of experiments. So if you do not follow any standard techniques, you'll be haphazardly doing a lot of experiments. So to guide your experiments, you can follow design of experiments. Okay, so there are several design of experiments you can follow, and then your the output of your experiments, the output of the experiments can be used statistically to obtain optimal, say, process operating conditions for your system. Now, similar thing can also be done with the techniques that we have been talking about as a part of this course. We talked about different optimization techniques, and if we have a model, mathematical model, which is a mathematical representation of the process. If you have a mathematical model for a process, that means a mathematical representation of a process, a set of equations which describe how the process behaves, then I can make use of this process. Then I make use of this mathematical model and make use of the suitable optimization techniques, some of the techniques we have already discussed here, and come up with the optimal operating conditions. So in that sense, yes, it is cost effective, and these days the process modeling, process simulation, and optimization plays a major role before we actually perform experiments and then design and operate an industrial process. It is cost effective. It is not only cost effective, it is not time consuming as well, because simulation will be much faster compared to experiments. There are simulations which also takes a lot of time, but definitely in general simulations are faster than compared to the experiments. Also, it depends on what kind of simulation we're doing. Say molecular simulations are time consuming as well. But for most of the times, for optimization, we will be looking for a model that reasonably describes the behavior of the process and doesn't take too much of time, so that I can make use of that process for optimization. The process models and optimization techniques are also useful for control purposes, online optimization, online control purposes as well. So to answer your question in one sentence, yes, optimization techniques are cost effective for any domain. In fact, not only chemical engineering or biomedical domains, for any domains. Okay, so with that, I'll come to the end of this session, and I take this opportunity to thank all of you for attending this course. I also take this opportunity to thank my TAs, Shreya Banerjee and Tinankur Kirtania, who are my students at IIT Kharagpur, for their effort, tremendous effort throughout this program. I'm also thankful to all my NPTEL colleagues for their extension of supports throughout the execution of this course. With that, once again, I urge you to stay safe, stay home, take care of your health, take care of your family. With that, thank you and goodbye.